guys, so we're going to get started again with log properties, and we quickly reviewed what these properties kind of look like. So remember that we just have 3 of them, where if you multiply the inputs, you can split up over the addition of 2 logs. If you divide those inputs, a divided by b, then you separate over subtraction. And if your input is raised to an exponent, then the exponent drops down in front and gets handled that way. So we did a couple of examples of expanding and contracting logarithms, but this time I'm going to open up with example 3, which is kind of a creative use of log properties. So take a look at each one of these examples, or look at the kind of introduction. We're allowing for r and t to be kind of new variables we're introducing, where r is equal to the log of 3 and t is equal to log of 15. And then we're asked to solve each of these problems in terms of r and t. So we're essentially rewriting each one of these logs in terms of r and t, which are defined as log of 3 and log of 15, respectively. So let's take a look at these. I'll tell you right now that in order to be successful, you have to be a little creative and let your brain kind of open up and enjoy these things. But my hint is that we are using log properties. So let's take a look at our first one here. Log of 45. So in order to kind of get an idea of where to go with this, look at the definition of r and t. R is a log of 3 and t is a log of 15. So is there a relationship between the number 45 and the numbers 3 and 15? Well, if you're thinking about this, you might notice that 45 is just the product 3 times 15. And now I see this like prime opportunity to start using our log properties. If I multiply the inputs, then I split that up over addition. And so this becomes log of 3 plus log of 15, and now I can directly substitute log of 3 is r and log of 15 is t. So I've taken my original log of 45 and rewritten it as the sum of r and t based on those definitions. Okay, so the second one, now that you kind of have an idea of how this works, see if you can figure out how to get a log of 5 in terms of r and t. You might want to pause the video and try that on your own, but I'll just go right into it. I noticed that 5 is the same as 15 divided by 3. So I'm going to rewrite this as 15 divided by 3. And based on my log properties, when you divide the inputs, you split that up over subtraction. So this would look like log of 15 minus log of 3. Log of 15 is the same as t. And log of 3 is r. And so that's this original log in terms of just t and r themselves. All right, how about our last one? I can see log of 15 already happening, which is kind of t here. And the third property I would be using is simply our exponent property, where that drops down to the front of the logarithm. So if I rewrite this to start, I might bring that square exponent down in front. So this becomes 2 log of 15. And now I can just directly substitute log of 15 as t. So this is 2t. Okay, so take a moment to kind of look through those problems and reflect on that ability to just be creative. The key here is understanding the original input, 45, 5, 15 squared, whatever that is. Understand that it can be decomposed into different parts, which are represented by the variables given there. And then that'll help you to be more successful with those types of problems. Okay, so moving on from log properties, I want to introduce a new type of logarithm, along with a new type of number that you may or may not have seen before. So we're going to talk about natural logs and the number e. So the number e is Euler's number, and it's approximately 2.718, but it's an irrational number, non-repeating, and very similar to kind of the number pi. So it's similar to pi in the sense that it is represented by a symbol, the letter E specifically, whereas pi is represented by the Greek letter pi. But it behaves just like a number, and you can treat it just like a number. So first I want to introduce the natural exponential function. So if we are looking at the natural exponential, It's represented as an exponential function with just a base of e. So it looks something like y equals e to the x power. And that's our natural exponential. So notice it's an exponential like normal, but the base here is e, so we call it a natural exponential. Okay. From this, we get a definition of a natural logarithm, which you're going to use a lot today. So a natural log, as you might have maybe guessed already, is just a logarithm with a base of e. So it's defined as, if I were to say y is equal to log with the base of e of the number x, then we actually use a more kind of sleeker version symbol. You're never ever going to write log base e like this. Instead, you'll write ln of x. So notice here I'm using the letters ln, natural logs here. Log with a natural base, I think is really why it's ln, is log with natural base e, so it's ln of x. And this is the symbol used to represent this idea, just the sense that we have a logarithm with a base of e. Okay, so now let's actually maybe do a couple of example problems where we're using the natural exponential function and a natural log. So first ones we're going to look at would be evaluating ln of e to the fifth power. So if I want to try to understand what the natural log of e to the fifth power is, I'm not entirely sure what this is equal to, so if that's ever the case, I set it equal to x, and then I just use my really good knowledge of logarithms to see what happens. So this is in log form, and I want to rewrite it in exponential form, in Ben form. So remember, that takes the base of the log, raise it to the exponent, and get the number back. So the base of this log is e, the exponent is x, and the number input is e to the fifth power. All right, well, now that I've written it in exponential form, it's pretty obvious to see that x is equal to 5. And if you're trying to find shortcuts and you notice, like, hey, taking the natural log of e to the fifth power, ultimately, natural log and e kind of cancel each other out, and you're left with the exponent 5. And that's not an accident, genuinely not an accident. Take a walk back over here with me. If I look at y equals natural log of x, I'm just going to write this down here as y equals natural log of x. Attempt and see if you can write this in exponent form. So that's a matter of taking the base, raised to the exponent, is equal to the number. So e to the y power is equal to the number x. Does this look familiar? Hopefully. Because it looks exactly like this one right here, y equals e to the x power, but the x and y's have been switched on each other. And you have probably done this before in integrated 3 when you were looking for inverse functions. Remember that if you wanted to find an inverse function, you would switch the x and y variables and then solve for y, and the result would be your inverse function. So what I'd like to point out here is simply that the natural log function y equals ln of x is the inverse to the natural exponential function y equals e to the x, and that's why in this situation it appears that they've kind of canceled each other out and you're left with the exponent 5. It's not an accident. Okay, let's try another example problem here. And I encourage you to pause the video and attempt to work this one out on your own. Okay, and my hint to you is start by rewriting this input, this number here, in terms of like a single e to a single power. So rather than having e in the numerator and denominator, attempt to rewrite this as a single power. Okay, so as you're maybe working that out on your own, I'll be working here. The cube root becomes a fractional power this way, and if I want to bring this term up, I simply make the exponent negative. So this would look like the natural log of e squared times e to the negative 5 halves power. 5/3. How about 5/3? And we can continue this work where it's e squared minus 5/3. So just when the bases are the same, that I add those exponents. And now if I'm thinking in terms of this last problem, the natural log and e ultimately cancel each other out. And my final answer is 2 minus 5/3, or more commonly known as 1/3. It's just common denominators here. 2 is really 6/3, so 6 minus 5 is 1/3. All right, now we're going to start working with a couple of examples that use the exponential function and the logarithm. Okay, so here's an example where the natural log is in the exponent of our function e. And again, if you're not really sure what this is equal to right off the bat, let's just set it equal to x and see what happens. All right, so now that we're in exponential form, I would recommend switching this into logarithm form and see if that helps you give or get a little closer to the answer here. So what I'm going to attempt to do is e is like the b raised to the exponent e, and this is my number n. So don't forget ben, right? Base to the exponent equals number. So if I want to rewrite this into log form, that's going to look like a log with base b, which is e, of the number n, which is x, is equal to the exponent in this problem, which is natural log of 3. But I know that log of the base e is just natural log. So this is actually natural log of x is equal to natural log of 3, and quite clearly I can see that x must be equal to 3. So, like in the last problem where the natural log and e canceled out, the same thing's happening here, where this e and natural log are canceling out, and I'm just left with the fact that x is equal to the input 3 in this case. All right, so example 4 looks a little bit more intense, but we're going to essentially be able to do the same thing with it that we did in example 3. So for this kind of a problem, notice that I have 2 logarithms in the exponent. Before I begin, I'm going to attempt to contract them into one logarithm. So first things first, any number out in front is indicative of an exponent on the input. So I can begin by rewriting this as e to the power of ln 8 to the 1/3 minus ln of 5. Okay, now a 1/3 power, that simply represents a cube root. What is the cube root of 8? It's just the number 2. Looking nicer already. Okay, when I subtract logs, that actually means that I'm dividing the inputs here. So this would look like e to the ln of 2 divided by 5. And the e and natural logs cancel. They are inverses of each other. So my answer is just the input 2/5. Okay, so that's all of our work with natural log and the number e. And so from here, we're going to start working on the change of base formula. So before we can begin talking about what the change of base formula actually is, I want to give you a little bit of motivation about why we use it and why it's powerful. So take a moment to consider the log with the base of 3 of the number 10. If I were to ask you to evaluate this logarithm, you might be able to give me a good guess here, but not an exact answer. And here's why. If I set this equal to x and rewrite it in exponential form, the question is really saying 3 to what power gives me 10? Well, 10 is very close to 9, so x is approximately 2 point something or other, but I don't know exactly what it is for sure. Also, if I attempt to do this with my calculator, I'll go to my calculator and see if I can find some logs. And the problem I run into is that my calculator only does log base 10 or log base e, natural log. It doesn't do log base 3 unless you have one of those modern fancy calculators that lets you set any base in the world, and that's awesome. But for the rest of us, we need to know the change of base formula, and this formula actually allows us to do some pretty cool things later on. Okay, so this is why we use the change of base formula. Now let's take a look at what it is. And I'm going to actually show you where it comes from because I think it's very helpful to know sort of that all of this makes sense with the log properties that you've already learned about. If I want to evaluate something like y equals log base a of some number x, like we did before, let's begin by just rewriting this in exponential form. So this would be like a to the y power is equal to the number x. Good start. But again, I'm not going to be able to solve this because it's not a simple solution. Much like 3 to the x equals 10 cannot be solved readily. So instead what I'll do is take the log of both sides. This is where I allow for each side of the equation to become the input for a log with a base that I choose. Now that's important. It can be any base that you choose. Commonly we're going to choose base 10 or base e because our calculators do those bases. But it could actually be any base you choose. So log base b of x. Notice that this side has become an input to the logarithm, and this side is also the input to this logarithm. That's called taking the log. Okay, let's go ahead and simplify. I know that exponents can fall down in front of the logarithm, so I'll rewrite this as y times log base b of a is equal to log base b of x. Now, ultimately, log base b of a is just a number, so I can finish solving this for y by dividing by that logarithm. So I get the result that y is equal to log base b of x divided by log base b of a. Okay, so what did we just do? Well, I started with an equation, y equals this, but I couldn't evaluate that. Taking the log, I found a result where I get the same number y, but using logs that have bases that my calculator can do, namely base 10 or base e, the natural logarithm. So this is called a change of base formula. Here's an easy way to remember it. In my original problem, notice how x appears to be a little bit taller than a, and this isn't like a mathematical way of doing this, but it just helps you to remember the formula a little better. The number that appears a little higher is on top, and this number a, the base, which appears to be lower on the logarithm, ultimately ends up on the bottom of the fraction. So that's how you can kind of remember how to do change of base correctly without mixing up, which one goes on top, which one's on bottom. So the one that's a little taller stays on top, the one that's a little lower goes on bottom. Okay, let's do a couple of examples using the change of base formula. So the first one is something kind of simple. It looks like log base 5 of 8. Okay, so clearly I can't just evaluate this in my head. There is no power of 5 that would give me an 8 back. Doesn't really make sense, or at least nothing, no whole number power, right? Let's use the change of base formula. The 8 is a little taller. That means that it stays on top. And the 5 is lower. That means it stays on the bottom of the fraction. And I want you to pause and think for a minute here. What base did I just choose? What base of logarithm did I choose? Well, there's nothing actually written, so remember that's a default of 10. So I've essentially used base 10. All right. Base 10 is something my calculator can do, so I will now use my calculator to evaluate this number. Take log of 8, hit equals, divide by log of 5, hit equals, and I get 1.292, approximately. This would be an exact answer. This is an approximate answer. I want to convince you that using any base would work. So I want you to do the same problem on your calculator again, but using natural logs. So ln of 8 divided by ln of 5. And what would that give me? Well, it should be the same number, but confirm that for yourself. So divide by natural log of 5. And yes, I get an approximation of 1.292. It is, in fact, the same number. Okay, example number 2. This one is a little, you could call it more challenging or not. Log base 4 of 1/9. Okay, go ahead and work on this on your own and then compare with my method here in the video. Okay, so I get an answer of negative 1.585. And this should be the same answer that you got. But did we do it the exact same way? When you entered your logarithm, did you take log of 1 over 9? Or did you do like I did with the negative 2 log of 3? You probably did log of 1 over 9. So where did I get my negative 2 over 3? Well, I like to include these types of things just to push your brains a little bit into thinking in terms of how can I rewrite this? Am I really getting the same answers? So check this out. The number 1 over 9 is actually the same as 3 to the negative 2 power. The negative would cause it to be a fraction, and the second power causes 3 to turn into 9. And if I'm taking the log of that now, well, I know that logs allow me to pull the exponent down in front. So that's why I'm getting this on the numerator here, and then this in the denominator here. And it's just a little bit of fun with exponents to show you that there are multiple ways to approach these problems. Okay, so now that we've gone over a couple of mechanical examples, I'm going to show you something that allows you to be more creative and use change of base in a very cool kind of a way. All right, so much like our previous examples with properties of logarithms where we had r and t introduced, and those required a lot of creativity, is kind of the same idea. You're going to allow yourself to be a bit creative, use the change of base formula, and then find results based on that. So take a second to read the problem, copy it down on your paper. It says that if log base x of 2 is equal to r, and log base x of 15 is equal to t, rewrite each in terms of r and t. So notice here that they don't actually define a base for you. They give you log base x, and x could really be anything. So why does that work? Well, the change of base formula works with any base. It doesn't have to be a specific base. So they're kind of just emphasizing for you by putting an x here that you could literally do this with any base and you're going to get the same answer. Okay, so let's attack some of these problems. We have log base 2 of 15. Well, if I'm going to evaluate this using change of base formula, then I might start by just applying, the top divided by bottom here. So this would look like something like log base, 10. I'll choose 10. I'm pretty happy with that. I'm also very lazy. I don't want to write anything extra if I don't have to. So I have log with a base of 10 of 15 and then log of 2. Now, they defined r to be log of 2 using any base, and t is log of 15 using any base. So the fact that I use 10 here is just fine. The numerator is equal to t, and the denominator is equal to r. So this is my final answer. Okay, now for the second problem, I actually need to do a little preliminary work first, where I need to contract the logs into one log, because notice that change of base formula only works if you have a single log in your problem. So let's start here. I know that addition means I'm going to multiply the inputs. So if I contract this log here, I get log base 8 of 15, which is perfect, because my 15 is something that I'm observing here as well. So now let's use change of base. This time, just for fun, I'm going to use the natural log, ln, then ln of 8. Okay, so I can see immediately that the numerator is just equal to t. Log base anything of 15 is equal to t. But what's happening in the denominator, log of 8? That doesn't appear to be a log of 2. Is it perhaps hiding? And hopefully you're thinking, well, yeah, 8's just 2 to the third power, right? So I can rewrite this as natural log of 15 all over natural log of 2 cubed. But exponents fall down in front of the logarithm, so I'm just going to do that right now and put that 3 down in front. Okay, now I'm at the perfect spot to start substituting, and I'm going to call the numerator is t. The denominator is 3 times natural log of 2, so 3 times r, in fact. 3r. And there's my answer for that one. So notice that you have to be a little creative, start using a couple of key steps here, like contracting the logarithms to begin with, but then jump right into change of base formula and see if you have to do a little work after that or be a little creative.